Hello again. On the next few videos, we're going to talk about concave up and concave down. And concavity is basically the concept here. And a function can be concave up on one particular open interval, and it can be concave down on another interval. But I've not even defined these terms yet. I understand that, but just bear with me for a second. Basically, a function, in particular, it's more the graph of the function that's concave up, and it's the graph of the function that's concave down. A graph is concave up informally if it looks like it's smiling, upward, along, in the positive y direction, and it's concave down if it looks like it's frowning in the in the negative y direction. In particular, a paradigm example is a classic parabola y equals x squared. It would be concave up everywhere from x equals negative infinity to x equals positive infinity. It smiles everywhere. Whereas the upside down parabola, y equals negative x squared, is frowning everywhere, because it's sort of frowning along the negative y axis, from along the domain of all real numbers. So that's what I mean. Those graphs are kind of boring because one smiles everywhere and one frowns everywhere. In general, other graphs, they'll smile here and they'll frown there. Like the sine, the sine and cosines, they smile in some places and frown in other places. So well, you may not know, but you'll learn. But you'll see that the sine and cosine, they'll smile on. Keep in mind that smiling and frowning, as we'll talk about later, I've not even told you what these terms mean yet, but just bear with me. Concave up is smiling, concave down is frowning. But here on the screen here, you see smiling and frowning. But what it is for concave up and concave down, these happen on open intervals. Guys, we need to have a sort of a context, a domain context. These happen in the domain context of open intervals. We need to have an open interval situation for these to happen on, okay? We don't want crazy examples. F double prime, it will be true that if F double prime is greater than 0 on an open interval, that we will be concave up on that open interval. But the native definition of concave up is this. The graph lies, you're concave up by definition if the smiling example, the smiling definition is good, but it's too informal. The real a more natural or a more formal definition, slightly more formal, I guess, is you're concave up if you lie above the graph of a function is concave up if it lies above its tangent lines. Like, take the paradigm example, y equals x squared. Pick any point on y equals x squared, the parabola. Draw a tangent line. The parabola lies above that tangent line in space, or on the page, in 2D space. Whereas, so y equals x squared lies above its tangents. It lies above all of its tangents. That's what it really means to be concave up. Now, as it turns out, it is true that for the parabola, y equals x squared, or f of x equals x squared, f double prime will equal the number 2. If you differentiate twice, if you differentiate x squared twice, you'll get, f double prime of x equals just the number 2. So f double prime will naturally be positive everywhere. And that will imply concave up. So as it turns out, that's just a pretty example. But even less pretty examples, it's true that if f double prime of x is greater than 0 on just some open interval, it doesn't have to be all real numbers, it doesn't have to be as pretty as all real numbers, but let's just say it's more restrained just on some open interval, then just for that open interval, f will be concave up on that open interval. And an analogous thing is true for concave down on the other hand, for concave down, the upside down parabola is the paradigm example for that one, So, there's other examples. Now, in a way, the model parabola and the model upside down parabola, they're kind of boring. one of them is always smiling, and one of them is always frowning. In other words, the paradigm parabola y equals x squared is concave up everywhere, and the upside down parabola y equals negative x squared, he is, concave down everywhere on the other hand. So, that's kind of boring. Now, the sines and cosine, like f of x equals sine x and f of x equals cosine x, they switch from smiling to frowning, smiling to frowning. In other words, concave up to concave down, back to concave up to concave down. They're much more interesting. So trig functions have more flavor, as we'll see later. Okay, so concave up is smiling, concave down is frowning. Now, keep in mind, f is the function that's concave up. In particular, it's the graph of f that's concave up. We just use f double prime as a litmus paper test. If f double prime is positive, that means the graph of the original function f is concave up. If f double prime is positive, the graph of the original function f is concave up and smiling. And if f double prime is negative, the graph of the original function f is concave down and hence frowning. Okay. Now, guys, again, and I need to be careful. Oops, bite my tongue here. If f double prime is positive on an open interval, the graph of the original function f on that open interval is concave up and smiling on that open interval. Again, we need to be in the context of an open interval. So I keep forgetting to say on an open interval. It gets annoying to keep having to say on an open interval every time, but I really should, to be, tit for tat, And so we're really smiling upward on that open interval, on that open interval. And it's annoying to have to tap that every time, but I don't want to confuse you and deceive you into thinking that it has to be everywhere when that's really not necessarily the case. It's the case for certain, nice functions, but it's not the case for everybody and every type of function, It's true for y equals x squared, but that doesn't mean it's true for everybody else. And I don't want to deceive you into thinking that that's always the case. So again, if f double prime is positive on a certain open interval AB, then the graph of the function f on that open interval AB is concave up, aka by definition, what we're saying is it lies above its tangents, and hence it looks like it's smiling along the positive y-axis on that open interval AB. It's concave up, and again, when I said concave up, I meant to say it's concave up on that open interval AB. Okay, that's what I meant to say. All right, and again, an analogous thing is true for concave down. You just you replace the word concave up with concave down, and it's going to be along the open interval AB, of course. And you replace smiling with frowning, and it's going to be along you're frowning down the negative y-axis. You replace positive y-axis with negative y-axis. It's just the analogous thing, and of course f double prime is now negative and not positive. It's the opposite situation. Well, I may as well read it off. If f double prime is negative for all x on that open interval, then f lies below its tangents on that open interval. And again, like here, f was above its tangents. Then f here, I guess I should say, instead of lies up here, lies kind of makes you think, you're below. Here, f, I guess rises would be the word up here, and down here would be the verb lies, just to keep the English good. So here you rise above your tangents, here you lie below, okay? But just on the open interval. You rise above your tangent lines just on that open interval AB. And if I didn't say that a minute ago, I should have. And down here, you lie below your tangent lines just on the open interval AB. Again, we need to be on the context of an open, and that interval is an open interval AB, okay? I want to be sure that's an open interval AB, lest there be any mistake. All right. And when I talk about concave up, and concave down on an open interval, it's the graph of f. It's not the graph of f prime. It's not the graph of f double prime. It's the graph of f. We're not really using f prime here really at all. And now f double prime, we're using it, but just as a litmus paper test. We're using f double prime, just so if it's positive on an open interval, if f double prime reveals a lot, if it's on an open interval. If it's positive on an open interval, it tells us a lot. We are concave up on that open interval. If it's negative on an open interval, we're concave down on that open interval. Okay. Well, if f double prime is positive on that open interval, then the graph of f is concave up on that open interval. And if f double prime is negative on that open interval, then the graph of the original f is concave down on that open interval. You kind of have to be careful how you say this. But anyway, so there's that. And I can't be careful enough how I say this. On the next few videos, I'm going to be much more cavalier. I'll read this definition again on the next few videos, but I was kind of, on the next video, I'm going to read these definitions again, but I'm kind of muddy and sloppy. The way I read the definitions now is the best way they should be read. On the next few videos, I start doing some examples and I read these definitions, but I do so in a much muddier and sloppier way. This, guys, the way I read the definitions on this video is the best way to read them. So write these down right now as they are. This is the way to read them. I wanted to sort of correct what I did this video. I'm not correcting what I did on the next video, but I'm sort of making less muddy. On the next video that I'm going to do, I was in a hurry to do some examples, and I kind of did the definition fast and loose. I did this video. I'm going to put this video in front of the videos I've already done. I made this prelude video after the fact in order to go back and soften my definition to make it rigorous, to make it tit for tat to where there'd be no confusion. This video is important and should not be ignored. This is an important video. Watch this video again. These definitions, I want you to get these definitions right. Don't mix up f double prime with f. So I just want you to get all this stuff right. Again, we're on the context of an open interval. And on the next few videos, I don't do a good job. I get my examples right, and the context of the examples kind of iron it all out anyway. I do a pretty good job. I do a good job on my examples. It's just when I lay down the definitions, I'm fast and I'm loose, and I needed to stick in a prelude video to fix that fastness and that looseness. I just wasn't happy. I wanted to get rid of the fast and the loose with my definitions. That needed to be fixed, in my opinion. And particularly an open interval. I kept saying interval, but I didn't say open interval. And, we were in the context of an open interval, and I needed to fix that, and I just wasn't happy. And I kept saying, well, f double prime being positive implied concave up. That's a sloppy thing to say. It's f double prime being positive on an open interval implied that the graph of f was concave up on an open interval. You need to really say it that way, because the open interval is the setting, the background where all this happens, and it's the graph of f that's concave up. So, guys, I've just given you some background there, and much needed background, in my opinion. This is important, and to me, not to be ignored, to say the least. So again, a concave up means that you rise above, the graph is above its tangents. That's the native definition. Well, and again, concave up on an open interval means that on that open interval, the graph of f rises above its tangent lines on that particular open interval. Okay. And then analogous concave down, the opposite is true on that open interval. The graph of f would fall below its tangent lines for that particular open interval. Now there's graphs that, on one particular open interval they'll be concave up, and on another particular interval they'll be concave down. On one particular open interval they'll be concave up, and on another particular open interval they'll be concave down. When we talk about concavity, guys, this is the concept, the topic of concavity. We need to use open interval, not just interval, open interval. Okay? The key word, open interval. When we talk about concavity, it's in an open interval, okay? Like the trig functions, cough, like they'll be concave up in this open interval and concave down in another open interval. Now, later on, we're going to talk about points called inflection points, where you switch from concave up to concave down, or vice versa. You switch from concave down to concave up. And as you might suspect, at an inflection point, F double prime is either going to go from negative to positive or from positive to negative. There'll be a little region, F double prime, to the immediate left of the inflection point. At the inflection point, F double prime will either be 0 or it will be undefined. It won't be anything else. Now, to the immediate left of the inflection point, F double prime will either be purely positive or purely negative. There'll be a little cluster of points to the immediate left where F double prime, in all those points, it'll be positive all the way for each point or negative all the way for each point. You won't have a mixture. It'll be one or the other. And then, let's just say positive. And then but then to the right, it'll be negative. So you switched. That's called I'm talking about F double prime. So F double prime went from positive to negative. So if F double prime, so did I say it right? I think so. So F double prime goes from positive to negative. My memory about went out on me. So F double prime was positive on the left side of the inflection point. Let's say let me go back. F double prime is, let's say we got an inflection point. Let's say to the immediate left of the inflection point, let's just say we got a domain X value. Let's say we got an inflection point. An inflection point's where remember, an inflection point is, or don't remember, I just told you, there's nothing to remember. This is brand new. I shouldn't use the word remember here. An inflection point's where the concavity changes, where you either go from concave up to concave down, or from concave down to concave up. So again, you either go from concave down to concave up, or concave up to concave down. In other words, F double prime goes from negative to positive or positive to negative. That's what an inflection point does for you. At the inflection point itself, F double prime will either go from negative to positive. At the inflection point itself, I was about to repeat myself. I was about to say something crazy. At the inflection point itself, back up. At the inflection point itself, F double prime will, at the inflection point, let's call it C. Let's call C the inflection point. F double prime of C, the inflection point C, F double prime of C will either equal 0 or it will not exist at all, aka it will be undefined. So, to the immediate left of the inflection point, will be either purely positive or purely negative, or F double prime will either be purely positive or purely negative. It'll be one or the other. And to the immediate right, it'll be the polar opposite, of what it was to the immediate left. So F double prime changes signs, when it crosses the inflection point. In other words, you go from concave up to concave down, or you go from concave down to concave up, just depending on the scenario. So it's a change of inflection point is the domain value where you change concavity. It's the X point where concavity changes. And of course, naturally, F double prime is going to change sign. It's either going to go from positive to negative or negative to positive. So that's, and you'll see, I'll define inflection point again on the next few videos. I'm out of time, guys. Thank you, and I'll see you on the next videos. Bye-bye.